So in today's session, we're going to be talking about optimizing for performance in Amazon CloudFront. Every millisecond counts. I'm Tino Tran. I'm a Principal Solutions Architect with AWS, specializing in edge services. And joining us on stage in a little bit will be Karthik Uthman, a Senior Software Development Engineer from our CloudFront engineering team, as well as a very special guest, Chris O'Brien, a Senior Engineering Manager from one of our customers at Tinder. So in today's session, we're going to be giving you an overview of the CloudFront global content delivery network. We're going to talk about some of the workloads that we see frequently from our customers before bringing Chris on stage to share Tinder's experience and some of the results they were able to achieve by using the service. After this, we're going to pull back the covers a little bit. We're going to take a look under the hood at some of the optimizations that we make and some of the things that we think about as we deploy our network. Right? So why don't we hop into it? Okay, so as I said before, CloudFront's our global content delivery network. And this slide right here basically gives you an eyeball view of our global presence. These little dots that you see on there are either points of presences or edge locations and, or AWS regions. Now, we're growing at a very rapid rate. Actually, last week we hit 210 points of presences around the world with our first one in Rome last week, actually. Every time I present this slide, I have to make sure it's up to date because we're always rolling out new edge locations. Of these 210 points of presences, we also have what we call regional edge caches, which is a mid-tier cache that sits between your origin servers and the edge locations around the world. The purpose of these regional edge caches is to reduce load on your origin, but also provide a better cache hit rate for your applications. This is baked into the network, and you get this as part of the service. There's no additional charge for it. The next thing you'll see here is there's lines around this graph, and between the edge locations and our AWS regions, we have a global backbone network that's privately managed by AWS. Later in the talk, I'm going to go into why this is significant and some of the things we think about as we deploy this backbone network. And we're growing at a very aggressive rate, 50% year over year. This is a trajectory we're hoping to continue into upcoming years. So next year when we come back, this slide will look drastically different. And because we're deploying our own infrastructure and managing our own network, we have the opportunities to do optimizations both at network and server layers. We're deploying our own hardware, and we'll talk more about that later on. Okay, so this session's called Optimizing for Performance in Amazon CloudFront, but let's take a step back a little bit and kind of set some context, right? Why does performance matter, and what are we hearing from our customers? Well, the first example I have here is a web page that's taking a long time to load. Right? We know on average a web page visitor will wait about 2 seconds for a page to load before they move on. And if your business depends on this website, it's not good, right? There's also a ripple effect to this. If your page takes too long to load, some of the crawlers out there that are used by search engines to index your websites will spend a certain amount of time on the page indexing it before moving on. If it takes too long to load, it's able to index less. It reduces your chances of showing up on search results. Also not good for business, right? The last example that we see more and more every day is the video streaming workloads. As the world's moving towards this over-the-top delivery platform for video delivery, for live and on-demand video delivery, we're starting to hear more from our customers that they want the capacity and scale required to support these workloads. They want their end users to have a good experience. They don't want buffering. They don't want any playback issues. And this is a big deal for these customers. So being a customer-obsessed company like AWS, these are also our motivations in providing good service to our customers. For me, there's a little bit of a cherry on top. I have a very demanding customer at home. My 4-year-old daughter, every time her video stream starts to buffer, she comes, knocks on my door and says, "Daddy, come play with me." Usually it's not a big deal, but when you work from home like I do sometimes, it's also not good for business, right? All right, so I talked about a few of the workloads, but we really have customers using us for all different workloads, from API acceleration to large file downloads like software updates, game patches. Of course, you have your static delivery, such as reports, images, files. But we also have a very cool feature built into the service called Lambda Edge. And what Lambda Edge is It's the ability to invoke Lambda functions on the request and response path of a CloudFront distribution. And in doing so, you can actually do things like render pages right there at the edge, right? And it's you're invoking Lambda functions that run Node.js or Python code, right? It's literally a full programmable language. Here are some of our customers. It's just kind of an eyeball view of some of the customers that have implemented the service successfully. I'm sure if you did a dig on some of the sites that you're surfing on the internet, you'll be able to find more, but this is kind of just to give you an eyeball view. We have customers in every industry using the service. For example, in media, we have Prime Video, Hulu, MLBAM, Sky News. Prime Video actually uses us to stream Thursday Night Football in over 200 countries around the world. Sky News actually recently used us to stream the royal wedding to 23 million viewers around the world. In financial services, we have customers like Intuit who rely on us for their content delivery, right? Slack also uses us. They're a messaging service that integrates with a number of communication platforms around the world. And they actually rely on us for API acceleration. So these are just some examples. And with that being said, I'm going to bring on stage Chris to share Tinder's experience in implementing the service and their journey.
Thanks, Tino. A match made in cloud. Hopefully that's the last of the puns, but no guarantees. I'm a senior engineering manager for Tinder. I work on the cloud infrastructure team, and we're responsible for making sure our customers have the best possible experience on the platform. Many of you probably know what Tinder is, but for some of you that don't, Tinder is the world's most popular app for meeting new people. With billions of matches to date, our size and scale means greater choice and access to a diverse set of matches. And so if you don't necessarily understand, maybe you've never used Tinder, maybe you understand what it is, but you don't necessarily have ever used it, let me walk you through some of the steps. So the first thing is to create a profile. You want to basically present your best self. Enter a short bio, set your location, specify your discovery settings for potential matches that you might be interested in meeting, and then upload photos. Let's go ahead and see it in action. So when you first log in, you'll be presented with a series of potential matches. You can see photos. You can also choose to dive a little bit deeper and read the person's profile and also look at some of the other photos they have. And then choose to either swipe left if you're not interested or swipe right if you are interested. If both of you swipe right, it's a match and you can get to chatting. You can share some laughs and maybe even set up a date. So what looks like a fairly easy, simple or intuitive app is actually very complex under the hood. There's multiple API calls that are happening at any given time for any of these different functions I just described. And all of them are happening over HTTPS, which means that there's a TLS handshake for every single call. The further the distance of the customer, the higher the latency that they may encounter. And so as I've kind of alluded to, many of our customers, especially far away from where our infrastructure is hosted in US East 1, could encounter latency issues. And so to maybe set a little bit more context around how that comes into play, let me just give you a high-level overview of our technical architecture. So we have a number of different clients, iOS, Android Web, that are all connecting over the internet to AWS and US East 1, where our backend infrastructure is hosted. And as I mentioned, all of these API calls need to establish the TLS handshake because it's happening over HTTPS. Some of you may remember this from school or studying for job interviews, but there's a lot that goes into a TLS handshake. There's a lot of information that needs to be exchanged. And so we thought, and it turns out that it was correct, that we might have an issue with this particular handshake, that it might be creating an excessive amount of latency for our customers, especially around the world. And so we started to measure some of this performance from our clients. And so these numbers are reported from our iOS clients as an average in these different countries. We have India that is over 700 milliseconds to establish this handshake. Germany, 470 milliseconds. Even the US, even just an average of the US is 210 milliseconds. And so with numbers this big, naturally the question is, how might we be able to address this latency? How can we reduce the latency? And so one thought that we had is, like Tino talked about, we could maybe leverage the Amazon CloudFront global presence. They have all these different points of presence throughout the globe. Maybe our infrastructure is hosted in US East 1, but CloudFront is much closer to the customer. But of course, CloudFront being a CDN, and we have dynamic content that is not cacheable, we didn't necessarily, the question we asked was, isn't CloudFront a CDN? Isn't that just for static content? And what we didn't realize at the time, but we realize today, is that there's actually proxy mode. Proxy mode gives us a number of benefits. We can terminate the TLS handshake geographically closer to the end user at the POP. We can reuse connections from the POP to our origin. And we can also use the optimized AWS global network to communicate from the POP to the origin instead of going over the slow internet. And so with that theory in mind, now it actually comes down to implementing it. And so just taking a quick step back, just another way to look at our technical architecture at a very high level. So we have all these clients, iOS, Android Web. They're connecting over the internet to Elastic Load Balancer that's hosted in US East 1. Behind that Elastic Load Balancer is a number of instances that are hosting the Tinder application. And so what we wanted to try to do is put CloudFront in the middle. Sure, the clients would still be connecting over the relatively slow internet, but they'd be connecting geographically closer. The CloudFront would have locations that would be terminated closer to the customer rather than having to traverse the internet to go all the way back to Virginia. And so obviously, having as many customers as Tinder does, things could potentially go wrong. Maybe our theory was not correct. Maybe we had a misconfiguration. And so we wanted to choose a test location to start, a test country. We wanted to have enough active users to have a conclusive result. We wanted to have a balanced distribution of iOS, Android, and web clients. And of course, the location should be as far as possible from US East 1 for the greatest improvement. It doesn't necessarily do us any good to perform a test in the United States. To kind of spoil, or to kind of break the suspense and spoil it, the country that we selected was Indonesia. But as I mentioned before, there's always the risk that things could go wrong. The theory could be wrong. We can make an error in configuration. And so how could we route a percentage of the traffic in Indonesia to Amazon CloudFront? And how can we roll back if CloudFront or the configuration has any errors? And so how we were able to do this was basically leverage Amazon Route 53 traffic policies. And the traffic policies allow us to basically layer a number of different record types or different types to accomplish exactly what I just talked about. We can have geography-based record entries to specify that it should only apply to Indonesia. We can have weight-based records to specify that only a percentage of the customers, in this case 25%, will be routed to CloudFront. And we can also leverage failover policy to respond quickly in real time if there's any challenges. So during the Indonesian test, we verified and tested configuration in the staging environments. We routed partial traffic, as I mentioned before, 25% in Indonesia to CloudFront. And of course, things don't always go smoothly. We thought that we anticipated every possible issue, but we did not. We encountered a few errors in our web clients, but with the traffic policies that I just described, then we were able to roll back easily and ultimately complete the deployment in 20 days. So, so this is the result. So this is as measured by our clients on average. So without Amazon CloudFront, this TLS handshake was being established in 550 milliseconds. And with Amazon CloudFront, this was being established in 70 milliseconds, which was a nearly 90% reduction. And that obviously makes the cloud infrastructure and Tinder engineering feel really good, but what does it mean for the customers? It actually means that app login, loading of profiles, image and video uploads are all 30 to 45% faster, and other APIs saw a performance improvement of 40 to 60% depending on the payload size. And with those results looking very promising, we wanted to go ahead and deploy it globally. We went country by country, again leveraging the Amazon Route 53 traffic policies, and ultimately we're able to roll out to all the countries around the world. And this is kind of a snapshot of the handshake latency before CloudFront. I showed this at the beginning. And this is what it is today. So in the case of India, which was 750 milliseconds, it's now, as it stands today, 50 milliseconds. The US was 210 milliseconds, and now it's 60 milliseconds. And so obviously, again, like the Tinder engineering feels really good about the results, but what is the actual impact to our customer base? And I think that the biggest takeaway is that it means more active users than before. And as I mentioned before, Tinder operates on its size and scale means that you get greater choice, access to more potential matches. And so naturally, with more customers on the platform, then that means potential more matches for new clients or returning customers or even existing customers. So users that were going away because of slower experience return to the application. And of course, the overall experience on the application is improved. Profiles are loading faster, and what that means, profiles are loading 20% faster, and we're also increasing activity on the application. Image uploads grew by 15%. Total swipers, which is left and right swipes, increased by 3%. And of course, overall browsing on the app was faster. So just to recap, Amazon CloudFront is for our dynamic workloads. We are experimenting with using CloudFront on our static content. In fact, our episodic series called Swipe Night, which some of you may have heard about, that happened 4 weekends in October, interactive series, that content was hosted on Amazon CloudFront. And we're going to continue to expand that throughout 2020. Ultimately, implementing Amazon CloudFront was simple and fast, and our API performance improved by 30 to 45%. And with that being said, I'm going to bring Tino back up on stage, and he could talk about some of the improvements under the hood that made that possible.
Thanks, Chris. Awesome. So now that we've shared with you some of the results that you're able to achieve by using our service, let's take a look under the hood, right? Let's take a look at our global network, and particularly in this part of the talk, we're going to be talking about our backbone network, right? So earlier, I showed you a slide that had the eyeball view of our global footprint, and I mentioned that between these edge locations and our AWS regions, we have a global backbone network that's privately managed by AWS, right? This backbone network is actually very significant to our service and provides us with a lot of ability to give our customers with consistent and reliable performance. And we're going to dive into detail about that. But before we go into that, I'm going to share with you how I like to think about it, because I'm more of like a visual person, right? So as a solutions architect, part of my job is to fly to different cities around the world and meet with our customers to help them design and architect their solutions, right? One of the challenges that I face when I arrive in these cities is I need to figure out how I'm going to get to their offices, right? I have a number of options. I could rent a car and maybe take the inside streets. If I'm lucky, I'll hit all the green lights and I'll get there on time, but usually you'll get red lights and I'll be late. In some cases, I might be able to take the highway, which is usually fast, but if I hit it at the wrong time of the day, I could hit rush hour. If there's a traffic accident, again, I'll be late. Now, in some of these cities, you have these very sophisticated metro systems or subway systems, right? And you can literally get off the airplane, out of the airport, walk down to the subway station, and hop on a train to get to where you need to go. It's usually great. It works. It's on time most of the time. And even if that one train that you're trying to use is down, there's usually a secondary line that you could take that also goes to the same destination, right? So with that, I'm able to reliably get to where I need to go without all of these outside factors. So to me, the backbone network is kind of like having a sophisticated metro system. It allows us to provide that reliable performance to our customers, right? And let's take a look a little bit deeper about some of those benefits. Okay, so I mentioned reliable performance, but the first point I want to talk about here is availability, right? Having a backbone network allows us to provide better availability in terms of that network path. And when I say that, I'm talking about path diversity. We want to ensure that we have multiple paths to get to the same destination once you're on our network. And by operating traffic on our own network, we're able to do things like understand different parts of the world where fiber cuts are more likely to happen, in which case we can lay down more fiber and ensure that we do have truly redundant paths. On top of that, we're also looking at capacity and scale, right? Operating traffic on our own network allows us to scale based off of our understanding of our customers' workloads, as opposed to relying on transit centers, who typically scale based off of traffic patterns that they've seen historically. If we had a customer that needed to drop a lot of traffic on our network, or on that network, it's not guaranteed to work, right? Because you'd be dependent on their capacity. The next thing is performance. So we're always monitoring and optimizing those paths from one point to another, but we're really not just thinking about the primary path, because we know that things break all the time, right? Fiber cuts happen, and we want to ensure that there's a reliable performance. So we're also measuring and monitoring our secondary paths, right? The third thing is proximity. Having a global backbone network allows us to be closer to our customers. In certain parts of the world, you're limited in the number of options you have for connecting to these networks. And having a backbone network allows us to open up our options. We can do things like do our own traffic engineering to route ingress and egress traffic to different cities. This helps us overcome things like congestion at certain internet exchanges or even sometimes peering disputes. And the last point is security. By having this global reach, we're actually reducing the number of networks between your end viewers and AWS infrastructure. And at the on-ramp to this global backbone network, our AWS POPs, we're doing things like DDoS detection. We're looking at bad signatures. We're filtering out malformed requests. Right? And once it's on the backbone network, it's infrastructure that we know and manage, where AWS takes responsibility for the security of it. Also worth mentioning is this backbone network is also used for cross-region traffic. So any region-to-region traffic only rides on the backbone network, with the exception of China. Okay, so I talked about the backbone network and the infrastructure on the backhaul, but how do we actually connect to the internet, right? The first way of connecting, that AWS connects to the internet is through our regional transit centers that sit within the AWS regions themselves. Networks can come and peer with us directly there. But we also have our points of presence, our edge POPs. These points of presences are the same edge locations where we deploy the CloudFront and other edge services like Route 53 and more, right? And when we're deploying these points of presences, what we're looking at and what we're thinking about is we want to be where the eyeballs are. We want to be where all the viewers are. The closer we are, the better. And in these cities where we deploy the POPs, what you'll typically find are these interconnect facilities, right, where networks can come and peer directly with one another. Within the same facilities, there's also these things called internet exchanges, where providers offer network switches that you could plug into and quickly access a large number of networks. We actually leverage both. We'll start with the internet exchanges, and as we learn more about the capacity that we need and scale that we need, we'll actually peer with those networks directly. And in doing so, this helps us scale our network connectivity for AWS and Amazon as a whole, and particularly CloudFront benefits from all of this network connectivity, right? It also allows us to kind of optimize for cost. When you use the CloudFront service, you're not paying for data transfer from an AWS region to the CloudFront edge location. You're paying for the data transfer out from the edge location to the public internet, which tends to be typically is a fraction of the cost of what it would be if you were going directly from the region. If you go to a website like PeeringDB, it's a public database of all of this network connectivity information. We're in over 100 facilities and connected to approximately 170 internet exchanges. This is all on the public internet. We also have private peering, which is not disclosed here. Okay, so that's the global infrastructure, that's the backbone network, right? In this part of the talk, I'm going to go over some of that last mile connectivity What are some of the optimizations we do from the viewer to our edge locations and back, right? And the first thing I'm going to share is our intelligent routing. And what I mean by that is the first thing that needs to happen when somebody makes an HTTP request is you need to tell them exactly where to go. And how that happens is they usually make a DNS query, right? So if I wanted to go to Tinder.com, I type that in on my browser. What's happening behind the scenes is we're making a DNS query to the local ISP resolver in most cases. If that resolver doesn't have the answer, it'll actually do a recursive query to our Route 53 servers. Now, in the case of CloudFront, Route 53 will actually recognize that, hey, this is a domain for CloudFront. So let's hand off the query to the CloudFront DNS servers that sit within our same location, right? And from there, CloudFront can dynamically figure out what's the most optimal POP to send that viewer to. And when it does that, it's actually looking at a number of factors. Because we learned that it's not about just sending your customers or your viewers to the nearest edge location. That's not guaranteed to give them the best performance. We're looking at a number of variables. We're looking at performance. When we talk about performance, we're actually measuring the round trip time of a TCP handshake from all of these viewer networks around the world to our different edge locations. And we take about 1 billion of these samples a day. It actually lets us understand at that point in time what the connectivity looks like, right? We can understand if there's network congestion and decide accordingly. The next thing that we're looking at is POP health. We want to make sure we don't send a viewer to an edge location that might be out of service to a hardware refresh, because we're always upgrading our servers, or to a location that is almost overwhelmed, right? We're also looking at server capacity. So within those edge locations, we want to make sure we have enough CPU, I/O, memory. We want to make sure that we have the processing power to process that request with the least amount of latency possible. And then the last thing that we're looking at is network connectivity. We're monitoring our links to these different networks, and we want to make sure that we're not sending traffic to edge locations that might be close to flooding their links, right? So with all that information, we can then come up with, provide an answer in real time to the client, and the client can then go ahead and make a connection. All right, so that was our intelligent routing. The next thing I was going to talk about is TCP congestion control. So performance is super important, and one of those factors is throughput, right? And this is the same TCP that you might have learned about in college. Being a CDN, we want to make sure that we're sending data back to the viewers or the clients as quickly as possible, and achieving the most optimal throughput on that last mile connection. Well, with TCP, ideally, the latency for the round trip of sending a packet from one point to another and getting it back would be the length of the pipe, right? However, if you notice on this diagram, some of those pipes are of different lengths because some of those routers along the way might have different bandwidth limits, right? If you send too much traffic, in some cases, some of those packets might get stuck in the buffer queue at one of those points along the way. And even worse than that, if you send way too much traffic, you might deal with a congestion event like packet loss. How TCP has been around a long time, and there's a lot of algorithms, congestion control algorithms that can be used to manage this, to determine, how many messages can be sent over that connection. Most of them rely on this packet loss event to determine, hey, do I need to scale down my congestion window, or do I want to go ahead and ramp it up more so I can achieve better throughput? When, for instance, a congestion control algorithm like Cubic will actually scale down and gradually ramp back up, right? At Amazon, we're always playing with these congestion control algorithms, and earlier this year, we deployed a new one called BBR, which was actually created by Google. And what BBR does is it manages the congestion control based off of actual congestion rather than packet loss. And how it does that is it's measuring the round trip time and the bandwidth limit along the path, right? It's looking for that bottleneck bandwidth limit. And the round trip time is ideally going to be the length of the pipe. So it's probing the network to identify what the most optimal round trip time should be, right? It's also probing for changes because traffic engineering happens, paths might change. So it also sends a bunch of packets to kind of identify if changes happened along that path. or the path changed and the bandwidth limit decreased or increased. So by doing this, it's able to kind of rapidly change the congestion window and adjust accordingly. And in doing so, its goal is to saturate the bottleneck limit, right? So that router along the way with the lowest amount of bandwidth, we want to send as many packets as possible up to that limit. Now, we actually seen some pretty good results when we rolled this out. Actually, one of our customers, Tutela, a service that monitors mobile networks around the world, actually reached out to us and said, hey, did you guys make any changes? All of a sudden, we saw a bunch of throughput on these CloudFront endpoints, and what's going on here? And the answer was yes, we rolled out BBR, a very simple change. We saw about 5 to 20% latency improvements, varying by POP and region. And most of these benefits come for networks that have a lot of packet loss, like your mobile networks. Right? Okay. So the next thing I'm going to talk about is TLS. So as more and more traffic is coming to the internet, right, more and more sensitive data is being shared, one of the standard ways of protecting that data in transit is using TLS. However, for customers, it can be challenging if you're trying to do this termination yourself because TLS is growing. We know that it's doubled over the past 3 years. It's actually, we see that it's close to 100% of our traffic. It also adds latency, and when you're a CDN and your job is to reduce latency for workloads, it's not a great thing because of that extra handshake. And then the versions are always changing because security is evolving and there's new versions coming out. So managing this is not something that customers really want to do themselves. They tend to offload this to the CDN like CloudFront. Right. So one of the things that we're rolling out, we're actively rolling out actually, is a library called S2N. S2N is an open source library, open sourced by AWS. And what it allows us to do is actually scope down the library to the focus of our use case, which is TLS, right? In comparison to something like OpenSSL, which is like 500,000 lines of code, we now only have to review about 6,000 lines of code with S2N. Now, this allows us to react quicker to security patches and deploy those types of changes. It also allows us to review the code with more scrutiny. Actually, in deploying this, we're already seeing less event blocking in our termination servers, right? Which gives us more capacity at our edge locations. Now, I mentioned that TLS comes at a cost, right? So it's this extra handshake that happens after the TCP handshake. And it's about 2 round trips, or it is 2 round trips. The first round trip is typically, you get the server certificate, you authenticate the server, and then you negotiate, what algorithms or what cryptography you're going to use to do the encryption on the subsequent messages. The second round trip is an exchange of these keys so that you can enable features like perfect forward secrecy. So there's value in that, but it comes at the cost of 2 round trips, and as you saw from Chris's slide, there's a lot happening there, right? And depending on how far your user is away from the edge locations, it'll affect your latency. But TLS also has a feature called session resumption, and this is something that we implement in CloudFront. So with session resumption, we're actually able to provide the client with a session ticket that the server would only know. It's a bunch of cryptographic information about the security profile of the original connection. And then on subsequent connections, when a client goes to resume a TLS connection, they can actually send the client hello with the session ticket. And in doing so, the server can validate that and reestablish the connection with the same security profiles that it had on the original connection. So now we're able to reduce one whole round trip from the initial, or from the subsequent TLS handshakes. Right. All right, so with that being said, I'm going to bring Karthik on stage to share some of the server-side optimizations.
Thank you, Tino. I'm Karthik. While I'm not giving talks about server optimizations, I'm actually at my desk trying to make our web servers better and make it faster. So that makes me an engineer. So Tino talked about all the network challenges we face and some of the optimizations we do on the network side. And because of that, we know that the request ended up on the best possible POP for your customers. In my part, I'll talk about the different optimizations we do on the server side and towards the origin while we fetch the content. Specifically, we'll talk about how do we optimize dynamic content and media workload, and lastly, we'll also talk about what do we do to reduce the load on your origins. So there was a internet code I read a while ago that there's only like two hard things when it comes to computer science. One is cache invalidations, the second one is naming things. I totally agree on the naming things part, but when it comes to caching, it's not just invalidations which is hard. It is everything about caching is hard. So as Tino and Chris mentioned, latency is super important. Like if you have bad latency, it leads to bad customer experience. So to make the latency better, what we have to do is cache the content in our servers. So when we serve the content right out of our cache servers, it's what we call a cache hit. And when the content is not in our cache servers, when we go and we have to go all the way to your origin server to fetch it, it's what we call a cache miss. So in order to provide the best possible experience, all we have to do is cache everything at our edge locations. But as you could imagine, the entirety of internet is so big that it is impossible to cache everything at our edge locations. So the first challenge is how do we effectively utilize our cache space? To understand that, we'll have to look into the edge location architecture. As you can see in the diagram here, each POP has an array of physical servers, and each of these servers have 3 layers of web proxies inside it. We call it the L1, L2, and L3. L1s act as a load balancer. It also has a little cache width. We call that the hot object cache. It's explicitly kept only for caching the really popular content. While the L2 is a cache width layer, the sole purpose of this layer is to just read and write from the cache. L3 does not have any cache space. It maintains a connection pool towards the origin, and we'll see the benefits of the connection pools towards the origin. So when a request lands in the L1 host, it looks at the configuration and to make sure that the request actually came for a valid customer, and it decides whether or not to satisfy that request. So once it decides to satisfy the request, it would do the TLS termination. And once it does the TLS termination, it would immediately look into the hot object cache. And if the content is not there in the hot object cache, it has to send the request to the L2 server, which is where the majority of our cache lies. But at this point, it can choose to send the request to any random L2 server. But if you do that, you're unnecessarily replicating the content, and your chance of getting a cache hit goes down drastically. So to solve that problem, what we do is we use consistent hashing algorithm to select peers. And we use the URL as the key for the consistent hashing. And as a result, if the same object lands on any of the L1 servers, they all would end up picking up the same L2. So we are optimizing for the cache hit rate, and we are also reducing the unnecessary redundant data storage in our cache servers. So for the sake of simplicity, let's assume that the content is not there in our L2 server, and it has to forward it to L3. But we know that the L3 does not have cache space. We have to optimize for connection pooling. So we do the same consistent hash peer selection, but in this case, we don't use the URL as the key. We use the origin domain as the key. So we send all the requests for a given domain to a single L3, and that way we get a good hit rate on the connection pools. And the L3 goes and fetches the content from the origin, and then we save it in our cache servers. So that's how our cache request workflow works. What about dynamic content? How did CloudFront help Tinder? How did we make Tinder use case much faster? So there are a couple of things. The first one is the TLS termination at the edge, very important. But apart from that, we also do when the request lands on the L1 server, we look at some of the distribution properties. For example, we look at the TTL you set in the distribution, and the different types of headers you want to forward to your origins. And these properties tell us that whether the response we get from your origin server is cacheable or not. And using that, we decide if it's a dynamic or a cacheable request. And if it ends up being a dynamic request, we skip all the cache layers, and then we directly go to the L3 layer. Well, so you might wonder, why do we have to go through the L3 layer? Why can't I go to the origin directly from L1? That's because the L3 layer provides two important functionalities which are really crucial for getting better performance. And those two are reducing the latency and improving your throughput. So why does this persistent connection give you these performance benefits? So to understand the latency part, let's look into the same three-way handshake that we have studied in our school, right? We know that to open a TCP connection, it does the three-way handshake, where we send a SYN, SYN-ACK, and a SYN. That takes about 1.5 round trip. And after that, you send the HTTP request on top of the open TCP connection, then you get the response. So the whole transaction takes about 2 RTT. But if you leave the connection open and send the subsequent request to the same origin on the same connection, you're getting the response back in a single RTT. So what we have done is we have effectively reduced our latency from 2 RTT to a single RTT. That's 50% improvement right there. The second part is the throughput. And to understand why we get better throughput on open connections or the persistent connections, we have to look a little bit into how the TCP congestion window works. Tino talked a lot about it already. So every TCP connection has a congestion window assigned to it. And this congestion window starts as a really small value, and it grows to the maximum possible value that the receiver says that it can handle. But it takes a while to grow to that maximum potential, and you'll get the best throughput only when the TCP congestion window grows to its maximum potential. So it takes a lot of time because of the way TCP works. It has the slow start phase, congestion avoidance phase. And if there's a packet loss in between, the congestion window would drop down again. So, and it's not going to go to the maximum capacity probably within the first request, so it might take a couple of requests. So reusing the connection again and again would give you better throughput over time. And combine this with the power of managed AWS backbone network, which has very few packet losses, then you're bound to get the best throughput possible. So that's dynamic content. So let's now look into the Tinder case exactly and how Tinder looked before they started using CloudFront. They had their origin in US East 1, AWS, and their customers, the test customers were in Indonesia. And when they opened the app, their request went all the way across the globe to the US East 1. And the request was at the mercy of multiple ISPs and their performance. So it literally took half a second to reach the servers in US East 1, which lead to slow termination and bad customer experience. But when Tinder met CloudFront, their customers didn't have to go all the way to the US East 1. Their request got routed to the nearest edge location. In this case, it ended up being Singapore. And the Singapore was just 70 milliseconds away. So your TLS got terminated right away. And when CloudFront had to forward the request all the way back to the US East 1, we sent it via our backbone network, and we were able to reach US East 1 from Singapore within 215 milliseconds. So the overall round-trip time reduced from like 500 milliseconds to like 285 milliseconds, which is about 40% savings in the latency right there. So if you love lower latency or you love getting your data faster, get matched with CloudFront. We're just a swipe away. So that's dynamic content. But we're not just for dynamic content. Our maximum workload is on cacheable and media content. In 2019 alone, we did a lot of large-scale media events. How many of you here are football fans? Do you guys watch Super Bowl? Yay. A couple of Seahawks fans, anybody? No? OK. So if you guys watched the Super Bowl last year, or if you live stream Thursday Night Football through Amazon Prime Video, there's a good chance that your content was delivered through CloudFront. Thursday Night Football, Prime Video streams that to about 18 million viewers worldwide. And even the Commonwealth Games, which happened last year, TV New Zealand streamed it through CloudFront to about 3 million viewers. This is awesome. But delivering live media does not come without challenges. There are multiple challenges in delivering live media content, but I'm going to talk about my favorite one. Let's go back to the Super Bowl day. we all gathered, we grilled some burgers, had some beer, having fun. But when the clock hit the game time, we stopped doing all that, and what do? We started watching the stream. Everybody started watching the same stream at the same time. So when this happens, we end up sending a bunch of requests to the same POP in that region. And this causes a unique problem in the CDN world, and we call this the flash crowd, or this is also commonly known as the thundering herd problem. So what does this flash crowd cost to the cache servers? So it's the same use case. A lot of people started watching Super Bowl at the same time, and all the requests got spread across our L1 servers. But as I mentioned before, these L1 servers are trying to optimize for hit rate, so they're going to forward the request to a single L2 using the consistent hashing mechanism. But this optimization works against us this time because it's going to overload that L2 server if it's going to take all that load. And that server is going to get overloaded, but the L1 servers, and eventually it will not be able to handle any more requests. But the L1 servers are still trying to send the content back to our customers, so it will try to send the request to another available L2, and the same thing is going to happen to that L2 server, and it continues, and this causes what we call a cascading failure inside our system. So to avoid this, we augmented our consistent hashing algorithm with a little bit more data. We gave it two properties. One is to track the popularity of the object that each L1 server is serving. And the second one is we also taught the L1s to learn about the load of each L2 server. So with this, when some of the L1 servers started sending the request to L2, it immediately learned that the L2 server is at its 95% load. So it can't handle any more requests. So it decides to send the load across the other available L2 servers. So even though you're replicating the content in a bunch of servers, it's kind of needed at this point to serve the content to our customers and keep the streaming going without any buffering issues. So that's great. But this is the first time that our viewers are watching this video, so nothing is in the cache. All these requests have to go down to the origin to get the content back. But if we forward all these requests down to the origin, we're going to see the same problem that we saw in the L2 server. We're going to start overloading the L3 server. But instead of spreading out the request again, the L2 servers are smart in the sense that they understand all the requests that are coming in at the same time is for the same object. So they decide to not forward all the requests. Instead, they forward just one request from each L2 server. So this eventually reduces a lot of load on the L3 server and also on your origins. And when it gets a response back for that one request, you would take that response and use that response to satisfy all the other requests that came for the same object. And when we get the response back, apart from satisfying all the other requests, the L2 layer would cache it immediately, because that's what the L2 layer does. It reads and writes from caches. And the response has to bubble up all the way to L1 and then to the viewers. But when it reaches the L1 knows the object popularity now. It is tracking it. And then it realizes this request is super popular. A lot of people are watching it. So it's a good idea to put it in my hot object layer. So it caches in the L1 layer. And from this point onwards, any other new customer who's watching the video stream from the beginning will not even reach the L2 to serve the content. We'll serve the content right away from our L1. And that's the best case possible for our customers. It provides the best latency and the throughput. So I mentioned we also work on reducing the load on your origins. But we have to understand why we had to go and do that. So we have 210 POPs today, and if we come and talk about CloudFront next year, it wouldn't be 210. I'm pretty sure it's going to be a way bigger number. And every year, we keep building more and more POPs, which means we're getting closer and closer to our customers, which is great because they get the lowest latency and the content is delivered much faster. But this also puts a different challenge on the origin side. As we build more POPs, if you have global viewership, the same content is being requested through all our POPs. That means if it was a cachement, it's going to your origins to fetch that content. So this puts a lot of load on your origin, and you might have to scale up your origin to meet up with the demands, or to scale up with the way that Amazon is scaling in terms of the POPs. So we wanted to avoid that. So we built a super POP. We called it the Regional Edge Cache. It's the mid-tier cache that sits between our POPs and your origins. And so after building the Regional Edge Cache, if there was a cache miss in our POP, instead of sending the request directly to your origin, it would send it to the Regional Edge Cache. Regional Edge Cache has like a humongous cache width, so it can save the content there for a way longer period than our regular POP can do. So this reduces a lot of latency for our customers and also reduces the load for them. So this is a graph of when we enabled Regional Edge Cache in India. Our latency, P90 latency reduced by like 20%, which is great. And I love this graph. This one shows the amount of bytes we serve on a daily basis from Regional Edge Cache. The blue line is the total amount of bytes. We serve about 12 petabytes from Regional Edge Cache every day. And out of the 12 petabytes, we only pulled 3.6 petabytes from our customer's origin. So which means we end up saving about 8.5 petabytes of data being pulled from our customers' origins on a daily basis, which is a big win for our customers. So to recap it all, Amazon is a global network. We have a year-over growth rate of about 50%. And as Chris mentioned, CloudFront is easy to deploy, super fast, and easy to manage. And AWS backbone network that comes along with most of our POPs provides a reliable performance to connect towards your origin. And we are always optimizing our infrastructure and service to provide you the best possible experience. And thanks to all these optimizations, Tino's daughter now can watch our video without any rebuffering issues, and he can be productive at home while working from home. So, and that's the same smile we want to see in all our customers' face, and that's why every millisecond matters. Thank you.